And now let's apply our general understanding regarding testing a hypothesis into doing some actual examples. And so now we are about to apply our understanding into testing a hypothesis about a mean value. So let's take a look at our example problems here. So in example A that we're currently having, so every example in this video lesson is one problem on its own, even though they may share some similarities regarding the given information. But in the end, each example itself is one problem on its own right here. So example A right here that we're looking at says a sample of 71 people gave mean breathing rates, and mean breathing rate here is a complete cycle in and out of 17.44 BPM, which stands for breaths per minute, and standard deviation 7.99 BPM. So at significance level 0.01 is the sample showing strong evidence that mean breathing rate is lower than 25 BPM. And so the main aim of this video here is to highlight at the steps being taken for testing a hypothesis problem, but we are going to skip a lot of the logical details, and all of those logical details that really explain the connections between the steps will wait into a higher course in statistics. And so right now, back into the wording of the problem itself, the experience that I want to point out here is that anytime we're doing a testing hypothesis problem, then very commonly the way how the question, the ultimate question, will be worded as a yes or no question. So is the sample showing strong evidence? And so that is immediately the question that brings to our attention that we're doing a testing a hypothesis problem. And then just like how I explained back in the general lecture regarding testing a hypothesis problem, then so now mean breathing rates, we want to prove that mean breathing rates is lower than 25 BPM. And so specifically, mean breathing rate is lower than 25. So now that immediately we can quickly sketch down the following understanding. Think about, we can assign mu here is to be the mean breathing rate. And so according to the wording, we want to look at the sample to see whether we have strong evidence for showing the mean breathing rate is lower than 25. So that immediately brings up for us an inequality statement. Mu is less than 25, and this is what we are proving. And so immediately in that way, our H1, the alternative hypothesis, as explained in the general lecture, will be recognized as mu is less than 25. This is our alternative hypothesis. And so once we have identified our alternative hypothesis, then null hypothesis can be easily recognized as simply the same statement, but replace the inequality by the equal sign. So mu equal 25 is what's recognized as our null hypothesis. And once we have identified the two hypotheses, then this particular problem here is to be recognized as a left tail. Right now it's a terminology, but we will get to see a little better of how this terminology will explain the procedure we are doing here. So right now the only impression I'm trying to show anybody is that as long as we have the inequality in the alternative hypothesis stating less than a value or less than the claim value, then we regard to this test as a left tail test. And let's look again at the wording description of our example and find out more about our available information regarding the sample. So a sample of 71 people, so this is clearly a sample, and we have here as a sample size that gave a mean breathing rate, and of course mean breathing rate is a complete cycle in and out of 17.44 breaths per minute, and a standard deviation of 7.99 breaths per minute. So these are all statistics of our samples. This is a sample mean and this is a sample standard deviation because it comes right out from these two values come right out from our sample. In other sample provided at the same sample size, we'll have very possibly different sample mean and a different standard deviation value. So again, in other words, what I'm saying now is that we already have for ourselves an available x bar being 17.44, and in the meanwhile, and at the same time, we are having 7.99 for our sample standard deviation. And so immediately, once we're looking at our sample mean value here, we are going to calculate a value that's so-called a t star value for our sample. And so the way to find a t star value for our sample mean is done as following. From where our sample mean stands, 7.44. And note that this sample mean we have is only one value among infinitely many other sample means existing out there, provided that we are at sample size 71. And so back to the work for finding t star. From where our particular sample mean value that we have, I'm going to subtract 25. So note where 25 came from. 25 is the value that's claimed in the null hypothesis. And this difference here will be divided by an expression that's 7.99 divided by square root of 71. So let me take a quick pause here and explain a little bit. So just like what I have explained earlier, this 25 came from the value being claimed in our null hypothesis. And 7.99 here came out from our sample standard deviation. And I'm talking about the 7.99 in the expressions at the denominator of this overall quotient here. And then the value 71 that stays inside of the square root is our sample size. And so we can quickly see a generality that's for any of the problem in testing a hypothesis. T star will always be calculated by the sample mean value that we're currently having. Subtract the value being claimed in the null hypothesis statement. And usually throughout many textbooks, that value being claimed, being stated in the null hypothesis is symbolically indicated as a mu sub 0. And we're dividing that by, now the fraction in the denominator here appears to be sample standard deviation divided by square root of the sample size. So this is a formula that's worth some good attention for any one of us viewing this video. And final calculation came out to be negative 7.972677 and a lot longer. And so now, unless being specified otherwise, usually throughout all of my examples in the video lectures, I will be rounding the t-score, the t-star value to 3 decimal places. But anyone viewing the video here is expected to watch out for your own rounding requirements in each problem that you are doing, that you are going through. So negative 7.973 is what I'm using here in the video. But as I said again, any one of us here viewing this video, when you're doing your own problem, make sure you watch for your own rounding requirements for each problem that you're working with. So T star here is negative 7.973. The sample that we're having, that we're using, and that's the only sample, being at sample size 71, will have a degrees of freedom. So formally it's called degrees of freedom. And degrees of freedom is in symbolic form, df will be calculated as sample size minus 1. So our degrees of freedom of this sample is going to be 71 minus 1, which gives me 70. And And so now that we are aware that our degrees of freedom of the sample here is 70, then we now can move on to the next step. The next step now is to calculate the p-value. The p here is usually short for probability. So it's a probability value. It's to indicate that we want to find the probability that among all sample mean existing out there. And now I'm back to using that capital letter X with a bar here. It's a random variable that represents a sample mean value. And specifically here, for my class, I always use a subscript 71 to indicate that any sample values that this random variable text here is a sample value that came from a sample of size 71. And that's what the subscript 71 is for. But so now, again, back to the formulation of the probability problem that I was halfway saying. And here we want to find the probability that among all sample mean values, we are looking for a sample mean being, now the problem here is a left tail test. So here I'm going to use the left tail inequality. I'm looking for the probability where a sample mean is below or less than or equal to 17.44. And so as a highlight point here, when we're setting up this probability problem, it's always, if it's a left tail that's indicated from the alternative hypothesis, then we will be writing a less than or equal inequality. And the value here will always be the value from the sample mean that we have. But now to calculate this value, to calculate this probability, we can start imagining that we are having a bell curve. And as I have said earlier, there are a lot of details, a lot of logical details are being skipped in this particular lesson. And then later on, when anyone viewing this video here arrive at a higher class and looking back at the same exact kind of problem here, then a lot more explanations will be explained at a higher class there that you're taking. But the bell curve here is to be the bell curve that represents all values of our sampling distribution of our sample mean at size 71. And this bell curve will have a center at 25, which is also the same with the value being claimed in a null hypothesis. And now this probability that we're calculating is the same as the area on this bell curve that's shaded to the left hand side. So 17.44 is for sure somewhere to the left side of our bell curve center. So 17.44 is our sample mean. But this probability here is to be understood as the area shaded to the left hand side of 17.44. So that's a couple of ways how we can check for consistency. Our test here is being regarded as a left tail test simply because that is an inequality that points to the left in the alternative hypothesis. And then another point to see how it's consistent is that once being a left-tailed test decided here, the t star score will come out being negative. And the way how we're setting up our probability calculation is involving the left tail inequality less than or equal. And then as a picture, we're shading to the left-hand side. That's why it's called left tail. The tail on the left of 17.44, our actual sample. So this black area shaded to the left-hand side of 17.44 is really the final p-value that we're attempting to calculate. So now to calculate this area, then even though we're on a bell curve, but we won't be able to find the sigma x bar of this bell curve. But even though without having this sigma x bar value, the average spread on this bell curve, we can still find the area here by firing up a program that's called TCDF command that can be commonly found in many standard graphing calculators. In this video lesson, I will be mainly staying with the standard TI 83 and 84, but this similar command right here will be available in many other software programs, including many other graphing calculators as well. So the p-value will be calculated by running that TCDF program. And so let's again look at the way how the picture is shaded. We have an interval here. This shaded area is in between an interval where we have an indefinite low end and a definite higher end right here at our sample mean value. And so now let me show that on the computer screen with the standard TI 8384 calculator. To find the TCDF command, I'm going to go second variables, which will bring up the menu for all the distribution functions in statistics. And TCDF is found at option number 6 right here. We can hit enter. Now, for the TI 83 users or some early 84 users, after calling the TCDF command, instead of seeing a menu like this one here, you will see the command being printed right on the home screen like this. And I will show how to use the command, how to operate with a command base like this later. But now let me get back on the version of the TI 83, TI 84 that I have here. So lower end here, as I said, is an indefinite lower end. So I'm going to go with -1 E99. And now I'm going to navigate down to the upper end of the interval here. And notice the command, the syntax that we're doing here, the command that we're doing here is called the TCDF. That means even though the interval here is written in terms of the x value, but here it's expecting the t-score, and that's the whole point of finding the t-score. And so, truly speaking, when we're using in our calculator, yes, lower end of the interval is an indefinite end, so it's -1 E99, but upper end here, instead of typing in 17.44, we have to type in the t-star value that we have calculated. So the t-star we calculated was -7.973. And I'm going to hit enter to proceed to the next line right here, which asks for the degrees of freedom. And here we're looking at 70 being our degrees of freedom. And I'm going to hit enter a few more times and getting ready for this command. And so now in that way of seeing how this command looks right here, then on the TI 83 or some of the earlier version of the TI 84, then instead of having a menu, if you are having a command line being printed directly on your home screen like this, right after you call up your TCDF command, then you can just go ahead and enter -1 E99 with a comma. So by far that's low end, and now with a comma. Now the high end, remember this is the command to operate on the T distribution. And so and hopefully this T in front of your command right here will remind you that every value here that you enter is a T value. And so now I'm going to have to enter -7.973. And then with another comma, and then the degrees of freedom. And now we're going to close the command. And now on this, back to my calculator that I'm using more regularly, then we're going to hit enter. So now recapping what we saw here, anytime you are running a TCDF command, either on the TI 83 or 84 or on similar technology or the technological devices, then usually it asks for the low end of your T interval. So here we're going to give a -1 E99, that's low end. and the high end is the t-score that we have found. And that's why it's always best to draw the picture of the bell curve, even though we're not using the normal CDF command, but here we use a tCDF command, even though we're still finding area shaded on the bell curve. So I also need to clarify, so this x bar value on this bell curve is equivalent to a t-score negative 7.973. So the t star there is about there. And so now negative 7.973 and the degrees of freedom. So for tCDF command, it requires to run with degrees of freedom, and that's why we had to calculate that ahead of time. 70. And now we're going to be ready for firing up the command. And as you have seen earlier on the computer screen, then the final p-value there, that lengthy value is in scientific notation. So let me write it down one more time. 1.024. The e minus 11 here from the computer screen means this is a 1.024 times 10 to the negative 11. So that e means a times 10. Exponential base 10, assumingly, on the computer, on the machines. And so this is 1.024 times 10 to the negative 11. But really that means this is, so our final p-value is concluded to be, and unless specified otherwise, I'll just round to 4 decimal places. So this means we're looking at 0.0000. So this is our final p-value. So now that our final p-value is 0.0000, and the p-value is graphically represented as the area shaded to the left of our x bar equals 17.44 on this bell curve, or shaded, or equivalently, this x bar value has corresponding t-score negative 7.973. And so the p-value for any testing hypothesis problem is to determine how unlikely a sample like what you have here will happen among infinitely many other samples out there. So look at the p-value here. I'm not saying that it's absolutely 0, but it's close enough so that even in 4 decimal places, it's like a 0 probability. And now to ensure that our p-value here will lead to strong evidence or not, we are going to compare this final p-value that we have calculated with the significance level. And significance level is usually indicated by an alpha symbol throughout many textbooks. But the comparison that I'm saying here is whether it's less than or greater than, whether our p-value is less than or greater than the significance level. And that's what we want to know. And so now one more time, looking back at the wording of the description on the computer screen here, then we do have a significance level given according to what it says right here, at significance level 0.001. So this is our significance level, or in other words, we have extracted another important information. Alpha equals 0.001. So that now means our final calculated p-value as a direct comparison with the given significance level 0.001. Our final calculated p-value here is well below the significance level given in a problem. So that now indicates as an interpretation that anytime we're having the p-value being less than the significance level, it means that our sample as an x bar being 17.44 is unlikely, meaning the sample we have like this, if we accept the null hypothesis saying that mu is 25, then it's unlikely to have a sample like what we have here. And being unlikely is making our sample, that's why it's leading to the sample itself is showing strong evidence. Or a lot of time for short, I would just say x bar is strong evidence. So showing here, the word showing here is just optional, but it's strong evidence. And strong evidence here is for us to say that we can reject whatever is stated in h sub 0. Or we can alternatively say we can support the alternative hypothesis argued in h1. And ultimately speaking, the question itself in the problem is a yes or no question. Is the sample showing strong evidence that mean breathing rate is lower than 25 breaths per minute? And here we already found that we had that x bar is showing strong evidence. So in that way, the final question ultimately will be yes. And now we're looking at example B among our examples as a different problem. And so let's now spend some time reading the wording description of our current problem here. So again, a sample of 71 people gave a mean breathing rate, a complete cycle in and out of 17.44 BPM, which stands for breaths per minute, and standard deviation 7.99 BPM. At significance level 0.001 is the sample showing strong evidence that mean breathing rate is higher than 10 BPM. So now on the writing board of mine right here, the wording of the question was asking, is the sample showing strong evidence that mean breathing rate is higher than 10 BPM? Mean breathing rate is higher than 10 BPM. And so with mu here is to represent the population mean breathing rate. As how many breaths per minute. Then the question was stating mean breathing rate is higher than 10. So mu is greater than 10. That's how we can translate that directly from the wording of the question. So mean breathing rate is higher than 10 BPM. And so now that means further that we can have for ourselves an alternative hypothesis stating as h1, saying that mu is greater than 10. And so now we can quickly identify our h sub 0 is a statement saying that mu is equal to 10 breaths per minute. And so this time the alternative hypothesis is having that inequality pointing to the right hand side. So in that way, this test we're about to do is called the right tail, or sometimes for short I call it the R-tail test. And let's now spend some time collecting the information from the sample here. A sample of 71 people and gave mean breathing rates of 17.44 BPM and standard deviation of 7.99. And so that immediately tells us that we have a sample size at 71. So our sample is having 71 people in it. And from this sample, we have a sample mean at 17.44. And we have a sample standard deviation to be lowercase s of 7.99. And so now from this sample that we have sketched some information here, then T star of our sample will be calculated as from where the sample mean stands, 17.44. We're going to subtract 10, which is the value that came out from the null hypothesis, and divide the difference there by a fraction 7.99 over square root of 71. And again, this t star calculation came out from the formula that, as a reminder, I can write it here. The x bar value that we have in our current sample, subtract the value being claimed in the null hypothesis and divide that difference there by a fraction expression, sample standard deviation s over square root of n, the sample size. Calculation came out for our t star score to be positive 7.846 and a lot longer. And unless being specified otherwise, a lot of times I will always round to my t star score to 3 decimal places throughout all of my video lectures here. So positive 7.846 is the final t star value. So this is the t score corresponding to our current sample mean value at 17.44. This sample at sample size 71 will have degrees of freedom, symbolically notated as df, to equal 71 minus 1. And this will be 70 for our degrees of freedom. And so now the next step to help deciding whether we have strong evidence for this test to support H1 is to calculate the p-value. And as a setup, our p-value here is calculated as the probability where among all sample mean values at size 71, we can find a sample mean where value is greater than or equal. So let me take a quick pause here. The test we have decided here is a right tail test. So now in a probability calculation setup right here, I'm going to use an inequality that points to the right hand side. And now I am going to be using this sample mean to complete our symbolic probability problem setup right here. So again, the statement here is saying that we want to find the probability that a sample mean at size 71 will be greater than or equal 17.44. And that's how we're setting up the calculation for our final p-value of our current sample. So after getting t star and degrees of freedom of our sample, the next step is immediately to find the p-value for our sample. And so now, getting into calculating the p-value, we can start imagining. Even though a lot of details, as I said earlier, must be skipped at our level of learning stats here, but these logical details can wait until anyone viewing this video will arrive at a higher course in statistics. But so now imagine that this bell curve here represents all possible values of our sample mean, of a sample mean at size 71. So it's a random variable, capital X bar 71. The center of this bell curve here now is actually at the value that's being claimed in the null hypothesis. So I'm putting 10 right here, right in the middle. So in that way, our sample mean value will be for sure somewhere to the right hand side of the bell curve center. That's our sample mean. And so now calculating this probability is the same as figuring out how big that area is shaded to the right hand side of our sample 17.44 on this bell curve. And look at how this area is being to the right hand side as a right tail right here. And that's another point to check for consistency between how we decide the test to be a right tail test and how we are proceeding into calculating the p-value. And now at this point, I have to also clarify that sigma x bar for this bell curve is unknown. And so this x bar, this particular x bar value on this bell curve, we will have t-score correspondingly positive 7.846. And so now to find this area or this probability on our current bell curve here, we are going to find that as by firing up or calling our TCDF command, which is provided in many standard calculators that comes with stat capability, including the standard TI-83 and 84. And so on my TI-84 calculator screen here, we call the TCDF command by hitting second variables and scroll down to option number 6 that says TCDF and hit enter to call that command right here. Now on the TI-83 calculator or many early TI-84 calculators, after calling the TCDF command, instead of a menu, you will see the command that's directly printed on your home screen like this. And I will get back to this and show how we can complete this command on the TI-83 calculator or the early TI-84 calculators. But now on the calculator that I'm using, so this time the lower and the high end of the interval here on the board, looking at the picture, we can see that in the way how this interval is shaded, then we have a definite low end but an indefinite upper end. And so for that reason, back on my computer screen, low end now is I'm going to use the value positive 7.846. And as I said, this program, this command is called TCDF, so the T here gives us a hint that it only takes all of these values are taken as t-score, as t values. So lower and upper are all t-score instead of the actual x-bar value. So don't put x-bar value into your TCDF command. We only put the actual t-score, and that's the reason why we spend our time finding t-score. So again, for lower, I'm entering 7 as a positive 7.846. Upper end is an indefinite upper end, so it's 1, positive 1, E99. Our sample is at degrees of freedom 70, so I'm putting 70 here, and I'm going to hit enter a few times, and now I'm ready for calculating the final answer here. So the same way on a TI-83 or early TI-84 calculators, then after your command is printed on the home screen this way, go ahead and open and type in your lower end of the t interval. So 7.846, and now with a comma, then the high end as 1 E99, and the next value here after the comma, after another comma, is 70 for degrees of freedom, and we close the parentheses, getting ready for action. Okay, so now for the actual calculation, let's now hit enter. Once our menu or command is completed, we're going to hit enter. So we have a value like this, and again, this is in scientific notation. So back to my writing board. Commonly speaking, TCDF command will run by taking a lower end on our t interval first. So in this case, lower end of the t interval is 7.846. The high end here is an indefinite high end, so on the TI calculator, we go 1E99. If viewers that's following this video is using a calculator other than the TI calculators, then read your own manual instruction for how to enter an indefinite end of an interval. And now, with another comma after upper end, I'm going to enter the degrees of freedom, being 70 for our testing procedure here. And so now the final answer that we have found there was in scientific notation 1.7548 and a lot longer, but the E minus 11 here from our standard TI calculator means the same as 1.7548 times 10 to the negative 11. That's what it means. In 4 decimal places, which is what I usually round it, our final p-value to, unless being specified otherwise, then we're only looking at a final p-value being 0.0000. So now that our final p-value is calculated to be 0.0000, this p-value decides for us how unlikely our sample will be, in the way that the null hypothesis claims the population mean is really at 10 BPM on this bell curve. And so to really decide, to make the final decision whether this p-value can tell us if we have a strong evidence sample, then we need to compare this p-value with our significance level. And again, significance level is given as an alpha symbol. We want to find out whether our p-value will be less than or greater than the significance level. So back to the reading of our problem right here, the line that says at significance level 0.001 is where we have our significance level given in a problem. And so that now means our final p-value is going to be compared directly with 0.001, the given significance level. And direct comparison now shows that our p-value is well below the significance level. So now having our p-value falling below the significance level is now sufficient to say that the sample that we're currently having is unlikely. It's unlikely to have a sample like this value. If the claim here truly is at 10, if we accept this claim here at mu equals 10, then our sample that we already had in hand is a very unlikely sample. It's very unlikely to have a sample like this one right here. And that's making the sample itself strong evidence. So now I'm saying that X bar is strong evidence or showing strong evidence. Two, either we can say we want to reject H sub 0, or another way of saying is to support H1. And again, the question to any testing hypothesis problem, as discussed in the general lecture, is always a yes or no question. And so the same is happening here. Is the sample showing strong evidence that? So our sample obviously shows strong evidence. So in that way, our ultimate final answer here is yes to the question. Yes, we have strong evidence.